Greetings everyone, my name is Gigi, and this is Let's Build, wherein I build a LEGO set timed to different media and talk about the facts concerning the topic of the build. Today's build is the LEGO International Space Station versus a documentary series, Astronaut Diaries, A Year in Space. I will not be playing any of the audio for copyright reasons. The documentary also goes into depth of the daily lives for the astronauts living and working on the ISS, the International Space Station, whereas I'm going to be focusing mostly on the structure itself. The footage I am using from the show is for science and educational purposes only. Specifications for the LEGO set. Build and display the spectacular LEGO Ideas ISS, the International Space Station. Packed with authentic ISS details, including a posable Canadarm2 and 2 rotating joints that coincide with 8 adjustable solar panels. This 864-piece set is a wonderful gift idea for space enthusiasts, adult LEGO fans, or any experienced builder. As a beautiful centerpiece, this awesome LEGO spaceship model comes with display stand, a buildable mini NASA space shuttle, and 3 mini cargo spacecrafts, plus 2 astronaut microfigures to create a striking centerpiece in any room. Illustrated instructions are included, plus a 148-page building instructions booklet with fascinating ISS facts and information about the LEGO fan who created this space model kit and its LEGO designer. The infinitely diverse array of LEGO Ideas sets are all created by LEGO fans and voted for by LEGO fans. Inspired by real life, action heroes, iconic movies, popular TV series, or totally original concepts, there is something to delight all ages. Challenge your construction skills with this LEGO Ideas ISS display model, featuring 2 rotating joints with 8 adjustable solar panels, posable Canadarm2, and other authentic details to discover as you build. This ISS model comes with a stand, 2 astronaut microfigures, a brick-built mini NASA space shuttle, and 3 mini cargo spacecrafts to create a spectacular display and rekindle nostalgic memories of childhood LEGO projects. Also includes a 148 building instructions booklet featuring fascinating facts about the International Space Station, the spaceship model's fan creator and LEGO designer, and a celebration of the LEGO Ideas theme's 10th anniversary. A super treat for yourself, birthday present or holiday gift idea for space fans, adults aged 16 plus, or any experienced LEGO builder. This 864-piece set offers hours of creative fun, whether built solo or with friends. This ISS toy building kit for adults measures over 7 inches high, 12 inches long, and 19 inches wide. It makes a beautiful display model that will catch the eye of every passerby. LEGO Ideas sets are created by LEGO fans and voted for by LEGO fans. Adults and children will be delighted by the infinitely diverse array of collectible construction toys for display and creative play. Many nations, shared intentions. It is truly astounding to think that nearly 16 times a day, the International Space Station orbits Earth on a continuous path of discovery. The space station is a truly international collaboration between 5 space agencies: NASA with the US, Roscosmos with Russia, JAXA for Japan, the ESA for Europe, and CSA for Canada. Utilizing their technological strengths, and participating countries work together under the umbrella of the International Space Station program to achieve common goals that benefit all humankind. Benefits: the 15 nations involved provide global leadership to advance human exploration, enable scientific research that benefits humanity, and establish a robust low Earth orbit economy. In parallel to achieving these goals, the partnership also includes the space station's unique platform to provide science, technology, engineering, and mathematics resources to educate the next generation of leaders and space explorers. Research in space. What happens on board this space station is also astonishing. The station has maintained a continuous human presence in space since November 2000. The astronauts on board have performed thousands of investigations dedicated to areas of Earth and space science, biology, human physiology, physical science, and technology demonstrations. As NASA states, the International Space Station is a state-of-the-art microgravity laboratory that is unlocking discoveries not possible on Earth and helping us push further into deep space. Research on this immense orbiting laboratory, the largest spacecraft ever built, is investigating how we can send humans further into space, to the Moon and Mars, to explore the frontiers of knowledge. Meet the fan designer. Christophe Rouge. In 2014, I got the idea to model the International Space Station using the LEGO Digital Designer. Since I didn't have the bricks to build it myself, I thought it would be cool if the LEGO group would do that instead. Once it was ready, I set up an entry on LEGO Ideas. The project was well appreciated in the community and had a good start. Nevertheless, it was a long way to reach the 10,000 votes. That gave me time to build the other space-related models and continue my research about the station itself. So I refined my model over and over again. In the end, it looked nothing like the first version I posted. I continued and didn't stop, even after the project finally reached the goal and got reviewed by the LEGO group. All in all, I had worked for more than 3 years on the first model and probably knew everything about the space station at the time. This research and knowledge became very handy when the Women of NASA set came onto the market. That was the moment I got the idea to do another version of the space station in the same scale as the shuttle included in this set. So I built a new model and set it up on LEGO Ideas. Again, it took a while to gather support and reach the review phase. Again, it got there, and again, it was rejected. But then I got the news that my earlier model had passed the special anniversary review to celebrate the 10th anniversary of LEGO Ideas, and that there would be a fan vote to determine which model would be built. That was very exciting. I can be very resourceful in terms of being patient and waiting for something when I think it is a good idea. But I can be pretty impatient as well. I think it is worth fighting for your dreams. I was overwhelmed when I got the news. Since the fan vote was a blind vote, I was only able to imagine how my chances were progressing. I felt sorry for the other 3 contestants. I would have loved to see Stitch produced as well. All in all, it felt quite unreal. LEGO designers Samuel Johnson, Crystal Fontaine, and Corvin Alexander Stitchert were the team who helped take the already awesome ISS design to the finish line, refining the design, working on the graphics, and ensuring that the original design met the LEGO requirements for stability and quality. The 10-year anniversary special review. The International Space Station was chosen as the winning LEGO Ideas set via a slightly different selection process than the normal Ideas set from LEGO. To celebrate 10 years of crowdsourcing and collaboration between LEGO Ideas, called LEGO CUUSOO until 2014, and LEGO fans around the world, we decided to dive into the archives of LEGO Ideas projects that had gathered 10,000 supporters but hadn't made it into production. There were over 130 projects which met that criteria, and that we believed could still make great LEGO Ideas products, as circumstances around their initial rejection had changed. From Hansen Jensen, Engagement Manager. We decided that one of these great ideas should be given a second chance, so we thought that we would turn the LEGO Ideas process upside down. This time we started the internal review and came up with 4 exciting projects that showed the greatest potential. And then it was up to the LEGO Ideas community to decide which of the 4 would be made into LEGO Ideas set number 29. It was great fun to follow the fan vote, and we were excited to be able to finally include the ISS into the LEGO Ideas family. From Monica Peterson, Global Senior Marketing Manager. Astronaut Dairies, Year in Space. An extraordinary, unearthly reality show from 2015 to 2016 is a YouTube series produced by TV channel Science 2.0, documenting the longest expedition at the ISS, made by the astronauts themselves, the space heroes, Mikhail Kornienko, sorry I butchered your name, and Scott Kelly. I started from episode 2 because that is when they arrive at the ISS. The ISS year-long mission, also called 1 Year Mission, was an 11-month-long scientific research project aboard the ISS, the International Space Station, which studied the health effects of long-term spaceflight. The NASA Twin Study was also conducted. Astronaut Scott Kelly is selected for the mission with his identical twin, Mark Kelly, on Earth as a control group. Scott spent 340 days in space for this experiment. The result demonstrated several long-lasting changes, including those related to alterations in DNA and cognition. The mission? Astronaut Scott Kelly and cosmonaut Mikhail Kornienko spent 340 days in space with scientists performing medical experiments. Kelly and Kornienko launched on 27th March in 2015 on Soyuz TMA-16M along with Gennady Padalka. Sorry, say your name wrong. The mission encompassed expeditions 43, 44, 45, and 46. The pair safely landed in Kazakhstan on the 2nd of March in 2016, returning aboard Soyuz TMA-18M with Sergei Volkov. The mission supported the NASA Twin Study, which helps shed light on the health effects of long-duration spaceflight. The goal aboard the orbiting laboratory was to understand better how the human body reacts and adapts to the harsh environment of space. Data from the mission was used to improve assessments of crew performance and health. They worked to develop and validate better countermeasures against the risks associated with future missions around the Moon, asteroids, and ultimately Mars. Moving on to the International Space Station. The ISS is a large space station that was assembled and is maintained in low Earth orbit by a collaboration of 5 space agencies and their contractors. NASA with the US, Roscosmos from Russia, ESA for Europe, JAXA for Japan, and CSA for Canada. As the largest space station ever constructed, it primarily serves as a platform for conducting scientific experiments in microgravity and studying the space environment. The station is divided into 2 main sections: the Russian Orbital Segment, or ROS, developed by the Roscosmos, and the U.S. Orbital Segment, USOS, developed by NASA, ESA, JAXA, and CSA. A striking feature of the ISS is the integrated truss structure, which connect the station's vast system of solar panels and radiators to its pressurized modules. These modules support diverse functions, including scientific research, crew habitation, storage, spacecraft control, and airlock operations. The ISS has 8 docking and berthing ports for visiting spacecraft. The station orbits the Earth at an average altitude of 400 kilometers, or 250 miles, and circles the Earth in roughly 93 minutes, completing 15.5 orbits per day. The ISS program combines 2 previously planned crew Earth orbiting stations, the United States Space Station Freedom and the Soviet Union's Mir 2. The first ISS module was launched in 1998, with major components delivered by Proton and Soyuz rockets and the Space Shuttle. Long-term occupancy began on the 2nd of November in 2000 with the arrival of the Expedition Crew 1. Since then, the ISS remained continuously inhabited for 24 years and 100 days, the longest continuous human presence in space. By March of 2024, 279 individuals from 22 countries has visited the station. Future plans for the ISS include the addition of at least one module, Axiom's Space Payload Power Thermal Module. The station is expected to remain operational until the end of 2030, after which it will be deorbited using a dedicated NASA spacecraft. As the space race drew to a close in the early 1970s, the US and USSR began to contemplate a variety of potential collaborations in outer space. This culminated in the 1975 Apollo-Soyuz test project, the first docking of spacecraft from 2 different spacefaring nations. The ASTP was considered a success, and further joint missions were contemplated. One such concept was the International Skylab, which proposed launching the backup Skylab B space station for a mission that would see multiple visits by both Apollo and Soyuz crew vehicles. More ambitious was the Skylab Salyut, the space laboratory, which proposed docking the Skylab B to a Soviet Salyut space station. Sorry if I'm saying that wrong. Falling budgets and rising Cold War tensions in the late 1970s saw these concepts fall by the wayside, along with another plan to have the space shuttle dock with a Salyut space station. In the early 1980s, NASA planned to launch a modular space station called Freedom as a counterpart to the Salyut and Mir space stations. In 1984, the ESA was invited to participate in Space Station Freedom, and the ESA approved the Columbus Laboratory by 1987. The Japanese Experiment Module, or GEM, or KIBO, was announced in 1985 as part of the Freedom Space Station in response to NASA request in 1982. In early 1985, science ministers from the European Space Agency, ESA, countries approved the Columbus program, the most ambitious effort in space undertaken by that organization at the time. The plans spearheaded by Germany and Italy included a module that would be attached to Freedom and with the capability to evolve into a full-fledged European orbital outpost before the end of the century. Increasing costs threw these plans into doubt in the early 1990s. Congress was unwilling to provide enough money to build and operate Freedom and demanded NASA increase international participation to defray the rising costs, or they would cancel the entire project outright. Simultaneously, the USSR was conducting planning for the Mir 2 space station and had begun constructing modules for the new station by the mid-1980s. However, the collapse of the Soviet Union required these plans to be greatly downscaled, and soon Mir 2 was in danger of never being launched at all. With both space station projects in jeopardy, American and Russian officials met and proposed that they be combined. In September of 1993, American Vice President Al Gore and Russian Prime Minister Viktor Chernomyrdin announced plans for a new space station, which eventually became the International Space Station. They agreed, in preparation for this new project, that the United States would be involved in the Mir program, including American shuttles docking in the Shuttle Mir program. The ISS was originally intended to be a laboratory, observatory, and factory while providing transportation, maintenance, and a low Earth orbit staging base for possible future missions to the Moon, Mars, and asteroids. However, not all of the users envisioned that the initial Memorandum of Understanding between NASA and Roscosmos have been realized. In 2010, the United States National Space Policy, the ISS was given additional roles of serving commercial, diplomatic, and educational purposes. The ISS provides a platform to conduct scientific research, with power, data, cooling, and crew available to support experiments. Small, uncrewed spacecraft can also provide platforms for experiments, especially those involving zero gravity and exposure to space. But space stations offer a long-term environment where studies can be performed potentially for decades, combined with ready access by human researchers. The ISS simplifies individual experiments by allowing groups of experiments to share the same launches and crew time. Research is conducted in a wide variety of fields, including astrobiology, astronomy, physical sciences, material sciences, science weather, meteorology, and human research, including space medicine and the life sciences. Scientists on Earth have timely access to the data and can suggest experimental modifications to the crew. If follow-on experiments are necessary, the routinely scheduled launches of resupply craft allows new hardware to be launched with relative ease. Crews fly expeditions of several months' duration, providing approximately 160 man-hours per week of labor with a crew of 6. However, a considerable amount of crew time is taken up by the station's maintenance. Perhaps the most notable ISS experiment is the Alpha Magnetic Spectrometer, or AMS, which is intended to detect dark matter and answer other fundamental questions about our universe. According to NASA, the AMS is as important as the Hubble Space Telescope. Currently docked on station, it could not have been easily accommodated on a free-flying satellite platform because of its power and bandwidth needs. On April 3, 2013, scientists reported that hints of dark matter may have been detected by the AMS. The space environment is hostile to life. Unprotected presence in space is characterized by an intense radiation field, consisting primarily of protons and other subatomic charged particles from the solar wind, in addition to cosmic rays. High vacuum, extreme temperatures, and microgravity. Some simple forms of life called extremophiles, as well as small invertebrates called tardigrades, can survive in this environment in an extremely dry state through desiccation. Medical research improves knowledge about the effects of long-term space exposure on the human body, including muscle atrophy, bone loss, and fluid shift. These data will be used to determine whether high duration of human spaceflight and space colonization are feasible. In 2006, data on bone loss and muscular atrophy suggested that there would be a significant risk of fractures and movement problems if astronauts landed on a planet after a lengthy interplanetary cruise, such as the 6-month interval required to travel to Mars. Medical studies are conducted aboard the ISS on behalf of the National Space Biomedical Research Institute. Prominent among these is the Advanced Diagnostic Ultrasound in Microgravity study, in which astronauts perform ultrasonic scans under the guidance of remote experts. The study consists of the diagnosis and treatment of medical conditions in space. Usually, there is no physician on board the ISS, and diagnosis of medical conditions is a challenge. It is anticipated that remotely guided ultrasound scans will have application on Earth in emergency and rural care situations where access to a trained physician is difficult. In August of 2020, scientists reported that bacteria from Earth, particularly Deinococcus radiodurans bacteria, I know I butchered that, I do apologize, which is highly resistant to environmental hazards, were found to survive for 3 years in outer space, based on studies conducted on the International Space Station. These findings supported the notion of panspermia, the hypothesis that life exists throughout the universe, distributed in various ways, including space dust, meteoroids, asteroids, comets, planetoids, or contaminated spacecraft. Remote sensing of the Earth, astronomy, and deep space research on the ISS have significantly increased during the 2010s after the completion of the U.S. orbital segment in 2011. Throughout the more than 20 years of the ISS program, researchers aboard the ISS and on the ground have examined aerosols, ozone, lightning, and oxides in the Earth's atmosphere, as well as the sun, cosmic rays, cosmic dust, antimatter, and dark matter in the universe. Examples of Earth-viewing remote sensing experiments that have flown on the ISS are the orbiting Carbon Observatory 3, ISS Rapid Scat, EcoStress, the Global Ecosystem Dynamics Investigation, and the Cloud Aerosol Transport System. The ISS-based astronomy telescopes and experiments include SOLAR, the Neutron Star Interior Composition Explorer, the Calorimetric Electronic Telescope, the Monitor of All-Sky X-ray Image, or MAXI, and the Alpha Magnetic Spectrometer. Gravity at the altitude of the ISS is approximately 90% as strong as at Earth's surface, but objects in orbits are in a continuous state of freefall, resulting in an apparent state of weightlessness. This perceived weightlessness is disturbed by 5 effects. 1. Drag from the residual atmosphere. 2. Vibration from the movements of mechanical systems and the crew. 3. Actuation of the onboard altitude control moment gyroscopes. 4. Thruster firings for altitude or orbital changes. And 5. Gravity gradient effects, also known as tidal effects. Items at different locations within the ISS would, if not attached to the station, follow slightly different orbits. Being mechanically connected, these items experience small forces that keep the station moving as a rigid body. Researchers are investigating the effect of the station's near-weightless environment on the evolution, development, growth, and internal processes of plants and animals. In response to some of the data, NASA wants to investigate microgravity's effects on the growth of the three-dimensional, human-like tissues and the unusual protein crystals that can be formed in space. Investigating the physics of fluids in microgravity will provide better models of the behavior of fluids. Because fluids can be almost completely combined in microgravity, physicists investigate fluids that do not mix well on Earth. Examining reactions that are slowed by low gravity and low temperatures will improve our understanding of superconductivity. The study of materials science is an important ISS research activity with the objective of reaping economic benefits through the improvement of techniques used on Earth. Other areas of interest include the effect of low gravity on combustion through the study of efficiency of burning and control of emissions and pollutants. These findings may improve knowledge about energy production and lead to economic and environmental benefits. The ISS provides a location in the relative safety of low Earth orbit to test spacecraft systems that would be required for long-duration missions to the Moon and Mars. This provides experience in operations, maintenance, and repair and replacement activities on orbit. This will help develop essential skills in operating spacecraft farther from Earth, reduce mission risks, and advance the capabilities of interplanetary spacecraft. Referring to the Mars 500 experiment, a crew isolation experiment conducted on Earth, the ESA states, whereas the ISS is essential for answering questions concerning the possible impact of weightlessness, radiation, and other space-specific factors. Aspects such as the effect of long-term isolation and confinement can be more appropriately addressed via ground-based simulations. Sergei Krasnov, the head of human spaceflight programs for Russia's space agency, Roscosmos, in 2011 suggested a shorter version of the Mars 500 that may be carried out on the ISS. In 2009, noting the value of the partnership framework itself, Sergei Krasnov wrote, "When compared with partners acting separately, partners developing complementary abilities and resources could give us much more assurance of the success and safety of space exploration. The ISS is helping further advance near-Earth space exploration and realization of prospective programs of research and exploration of the solar system, including the Moon and Mars. A crewed mission to Mars may be a multinational effort involving space agencies and countries outside of the current ISS partnership. In 2010, ESA Director General Jean-Jacques Dordain stated his agency was ready to propose to the 4 other partners that China, India, and South Korea be invited to join the ISS partnership. NASA Chief Charles Bolden stated in February 2011, "Any mission to Mars is likely to be a global effort." Currently, U.S. federal legislation prevents NASA cooperation with China on space projects without approval by the FBI and Congress. The ISS crew provides opportunities for students on Earth by running student-developed experiments, making educational demonstrations, allowing for student participation in classroom versions of ISS experiments, and directly engaging students using radio and email. ESA offers a wide range of free teaching materials that can be downloaded for use in classrooms. In one lesson, students can navigate a 3D model of the interior and exterior of the ISS and face spontaneous challenges to solve in real time. The Japanese Aerospace Exploration Agency, or JAXA, aims to inspire children to pursue craftsmanship and to heighten their awareness of importance of life and their responsibilities in society. Through a series of educational guides, students develop a deeper understanding of the past and near-term future of crewed space flight, as well as that of Earth and life. In the JAXA Seeds in Space experiments, the mutation effects of spaceflight on plant seeds aboard the ISS are explored by growing sunflower seeds that have flown on the ISS for about 9 months. In the first phase of Kibo utilization from 2008 to mid-2010, researchers from more than a dozen Japanese universities conducted experiments in diverse fields. Cultural activities are another major objective of the ISS program. Tetsuo Tanaka, the director of JAXA's Space Environment and Utilization Center, has said, There is something about space that touches even people who are not interested in science. Amateur Radio on the ISS, or ARIS, is a volunteer program that encourages students worldwide to pursue careers in science, technology, engineering, and mathematics through amateur radio communications opportunities with the ISS crew. ARIS is an international working group consisting of delegations from 9 countries, including several in Europe, as well as Japan, Russia, Canada, and the United States. In areas where radio equipment cannot be used, speakerphones connect students to ground stations, which then connect the calls to the space station. First Orbit is a 2011 feature-length documentary about the film Vostok 1, the first crewed spaceflight around the Earth. By matching the orbit of the ISS to that of the Vostok 1 as closely as possible in terms of the ground path and time of day, documentary filmmaker Christopher Riley and ESA astronaut Paolo Nespoli were able to film the view that Yuri Gagarin, sorry if I've been butchering names, saw on his pioneering orbital space flight. This new footage was cut together with the original Vostok 1 mission audio recordings sourced from the Russian State Archive. Nespoli is credited as the director of photography for this documentary film, as he recorded the majority of the footage himself during Expedition 26 and 27. The film was streamed in a global YouTube premiere in 2011 under a free license through the website firstorbit.org. In May 2013, Commander Chris Hadfield shot a music video of David Bowie's Space Oddity on board the station, which was released on YouTube. It was the first music video filmed in space. In November 2017, while participating in Expedition 52 and 53 on the ISS, Paolo Nespoli made 2 recordings of his spoken voice, one in English and the other in his native Italian, for use on Wikipedia articles. These were the first content made in space specifically for Wikipedia. In November of 2021, a virtual reality exhibit called The Infinite, featuring life aboard the ISS, was announced. The International Space Station is a product of global collaboration with its components manufactured across the world. The module of the Russian orbital segment, including Zarya and Zvezda, I hope I said that right, probably didn't, were produced at the Korechnev State Research and Production Space Center in Moscow. Zvezda was initially manufactured in 1985 as a component for the Mir 2 space station, which was never launched. Much of the U.S. orbital segment, including Destiny and Unity modules, the integrated truss structure and solar arrays were built at NASA's Marshall Space Flight Center in Huntsville, Alabama, and McLeod Assembly Facility in New Orleans. These components underwent final assembly and processing for launch at the Operations and Checkout Building and the Space Station Processing Facility at the Kennedy Space Center in Florida. The U.S. orbital segment also hosts the Columbus module, contributed by the European Space Agency and built in Germany. The Kibo model was contributed by Japan and built at the Tsukuba Space Center and the Institute of Space and Astronautical Science, along with the Canadarm2 and Dextre, a joint Canadian-U.S. endeavor. All of these components were shipped to the SSPF for launch processing. The assembly of the International Space Station, a major endeavor in space architecture, began in 1998 of November. Modules in the Russian segment launched and docked autonomously, with the exception of Resvet. Other modules and components were delivered by the Space Shuttle, which then had to be installed by astronauts either remotely using robotic arms or during spacewalks, more formally known as extravehicular activities or EVAs. By the 5th of June in 2011, astronauts had made over 159 EVAs to add components to the station, totaling more than 1,000 hours in space. The foundation for the ISS was laid with the launch of the Russian-built Zarya module atop the Proton rocket on the 20th of November in 1998. Zarya provided propulsion, altitude control, communications, and electrical power. 2 weeks later, on the 4th of December in 98, the American-made Unity was ferried aboard the Space Shuttle Endeavour on STS-88 and joined with Zarya. Unity provided the connection between the Russian and U.S. segments of the station and would provide ports to connect future modules and visiting spacecraft. While the connection of the two modules, built on different continents by nations that were once bitter rivals, was a significant milestone, these two initial modules lacked life support systems, and the ISS remained unmanned for the next 2 years. At the time, the Russian station Mir was still inhabited. The turning point arrived July 2000 with the launch of the Zvezda module. Equipped with living quarters and life support systems, Zvezda enabled continuous human presence aboard the station. The first crew, Expedition 1, arrived that November aboard Soyuz TM-31. The crew grew steadily over the following years, with modules delivered by both Russian rockets and the Space Shuttle. Expedition 1 arrived midway between the Space Shuttle flights of missions STS-92 and STS-97. These two flights each added segments of the station's integrated truss structure, which provided the station with Q-band communications, additional altitude control needed for the additional mass of the USOS, and additional solar arrays. Over the next 2 years, the station continued to expand. A Soyuz U rocket delivered the Pirs docking compartment. The Space Shuttles Discovery, Atlantis, and Endeavour delivered the American Destiny Laboratory and Quest airlock, in addition to the station's main robot arm, the Canadarm2, and several more segments of the integrated truss structure. Tragedy struck in 2003 with the loss of the Space Shuttle Columbia, which grounded the rest of the shuttle fleet, halting construction of the ISS. Assembly resumed in 2006 with the arrival of STS-115 with Atlantis, which delivered the station's second set of solar arrays. Several more truss segments and a third set of arrays was delivered on STS-116, STS-117, and STS-118. As a result of the major expansion of the station's power generation capabilities, more modules could be accommodated, and the U.S. Harmony module and Columbus European Laboratory were added. These were soon followed by the first two components of the Japanese Kibo Laboratory. In March of 2009, STS-119 completed the integrated truss structure with the installation of the fourth and final set of solar arrays. The final selection of Kibo was delivered in July 2009 on STS-127, followed by the Russian Poisk model. The U.S. Tranquility module was delivered in February 2010 during STS-130 alongside the Cupola, followed by the penultimate Russian module, Razvet, in May 2010. Razvet was delivered by Space Shuttle Atlantis on STS-132 in exchange for the Russian Proton delivery of U.S.-funded Zarya module in 1998. The last pressurized module of the USOS, Leonardo, was brought to the station in February of 2011 on the final flight of the Discovery STS-133. Russia's new primary research module, Nauka, docked in July 2021, along with the European robotic arm, which can relocate itself to different parts of the Russian modules of the station. Russia's latest addition, the Prichal module, docked in November of 2021. As of February 2025, NASA.gov states that there are 43 different modules and elements installed on the ISS. The pressurized modules include Zarya, also known as Sunrise, also known as the functional cargo block, was the integral component of the ISS. Launched in 1998, it initially served as the ISS power source, storage, propulsion, and guidance system. As the station has grown, Zarya's role has transitioned primarily to storage, both internally and in its external fuel tanks. A descendant of the TKS spacecraft used in the Salyut program, Zarya was built in Russia but is owned by the United States. Its name symbolizes the beginning of a new era of international space cooperation. The Unity module. Unity, also known as Node 1, is the integral US-built component of the ISS. Serving as the connection between the Russian and US segments, this cylindrical module features 6 common berthing mechanism locations: forward, aft, port, starboard, zenith, and nadir, for attaching additional modules. Measuring 4.57 meters in diameter and 5.47 meters in length, Unity was constructed of steel by Boeing for NASA at the Marshall Space Flight Center in Huntsville, Alabama. It was the first of 3 connecting nodes, Unity, Harmony, and Tranquility, that forms the structural backbone of the U.S. segment of the ISS. Okay. The Zvezda. I do not know if I'm saying that right. Or also known as Star, launched in July of 2000. It is the core of the Russian orbital segment of the ISS. Initially providing essential living quarters and life support systems, it enabled the first continuous human presence aboard the station. While additional modules have expanded the ISS's capabilities, Zvezda remains the command and control center for the Russian segment, and it is where crews gather during emergencies. A descendant of the Salyut program's DOS spacecraft, Zvezda was built by RKK Energia and launched atop a Proton rocket. The Destiny Laboratory is the main research facility for U.S. experiments on the ISS. NASA's first permanent orbital research station since Skylab, the module was built by Boeing and launched aboard the Space Shuttle Atlantis during STS-98. Attached to Unity over a period of 5 days in February of 2001, Destiny has been a hub for scientific research ever since. Within Destiny, astronauts conduct experiments in fields such as medicine, engineering, biotechnology, physics, materials science, and earth science. Researchers worldwide benefit from these studies. The module also houses life support systems, including oxygen generating system. The Quest Joint Airlock enables extravehicular activities, or EVAs, during using either the U.S. Extravehicular Mobility Unit, EMU, or the Russian Orlan spacesuit. Before its installation, conducting EVAs from the ISS was challenging due to a variety of system and design differences. Only the Orlan suit could be used from the transfer chamber on the Zvezda module, which was not a purpose-built airlock, and the EMU could only be used from the airlock on a visiting space shuttle, which could not accommodate the Orlan. Launched aboard the Space Shuttle Atlantis during STS-104 in July of 2001 and attached to the Unity module, Quest is a 6.1 meter long, 4 meter wide structure built by Boeing. It houses the crew airlock for astronaut egress, an equipment airlock for suit storage, and has facilities to accommodate astronauts during their overnight pre-breathe procedures to prevent decompression sickness. The crew airlock, derived from the space shuttle, features essential equipment like lighting, handrails, and an umbilical interface assembly that provides life support and communication systems for up to two spacesuits, simultaneously. These can be either two EMUs, two Orlan suits, or one of each design. Poisk, Russian for search, also known as the Mini Research Module 2, serves as both a secondary airlock on the Russian segment of the ISS and supports docking for Soyuz and Progress spacecraft, facilitates propellant transfers from the latter. Launched on the 10th of November in 2009, attached to a modified Progress spacecraft and called Progress M-MIM2. Poisk provides facilities to maintain Orlan spacesuits and is equipped with two inward opening latches, a design change from Mir, which encountered a dangerous situation caused by an outward opening hatch that opened too quickly because of a small amount of air pressure remaining in the airlock. Since the departure of Pirs in 2021, it's become the sole airlock on the Russian segment. Harmony, or Node 2, is the central connecting hub of the U.S. segment of the ISS, linking the U.S., European, and Japanese laboratory modules. It's also been called the Unity Hub of the ISS as it provides essential power, data, and life support systems. The module also houses sleeping quarters for 4 crew members. Launched on the 23rd of October in 2007 aboard Space Shuttle Discovery on STS-120, Harmony was initially attached to the Unity before being relocated to its permanent position at the front of the Destiny Laboratory on November 14, 2007. This expansion added significant living space to the ISS, marking a key milestone in the construction of the U.S. segment. Tranquility, also known as Node 3, is a module of the ISS. It contains environmental control systems, life support systems, a toilet, exercise equipment, and an observation cupola. The European Space Agency and the Italian Space Agency had Tranquility manufactured by Thales Alenia Space. A ceremony on November 20th, 2009 transferred ownership of the module to NASA. On February 8th, 2010, NASA launched the module on the Space Shuttle's STS-130 mission. Columbus is a space laboratory that is part of the ISS and is the largest single contribution to the station made by the European Space Agency. Like Harmony and Tranquility modules, the Columbus Laboratory was constructed in Turin, Italy by Thales Alenia Space. The functional equipment and software of the lab were designed by EADS in Bremen, Germany. It was also integrated in Bremen before being flown to the Kennedy Space Center in Florida in an Airbus Beluga jet. It was launched aboard Space Shuttle Atlantis on February 7th of 2008 on flight STS-122. It is designed for 10 years of operation. The module is controlled by the Columbus Control Center, located at the German Space Operations Center, part of the German Aerospace Center in, I am not going to say this right, Oberpfaffenhofen, near Munich, Germany. Apologies for saying that wrong, probably. The European Space Agency has spent over $1.4 billion on building Columbus, including the experiments it carries and the ground control infrastructure necessary to operate them. Kibo, or in Japanese HOPE, also known as the Japanese Experiment Module, is Japan's research facility on the ISS. It is the largest single module on the ISS, consisting of a pressurized lab, an exposed facility for conducting experiments in the space environment, 2 storage compartments, and a robotic arm. Attached to the Harmony module, Kibo was assembled in space over 3 space shuttle missions: STS-123, 124, and 127. The Cupola is an ESA-built observatory module of the ISS. Its name derives from the Italian word cupola, which means dome. Its 7 windows are used to conduct experiments, dockings, and observations of the Earth. It was launched aboard Space Shuttle mission STS-130 on the 8th of February in 2010 and attached to the Tranquility module. With cupola attached, ISS assembly reached 85% completion. The cupola's center window is a diameter of 80 centimeters, or 31 inches. Razvet, also known as First Light, also known as the Mini Research Module 1, and formerly known as the Docking Cargo Module, is primarily used for cargo storage and as a docking port for visiting spacecraft on the Russian segment of the ISS. Razvet replaced the cancelled docking and storage module and used a design largely based on the Mir docking module built in 1995. Razvet was delivered in May 14th of 2010 on the Space Shuttle Atlantis on STS-132 in exchange for the Russian Proton delivery of the US-funded Zarya module in 1998. Razvet was attached to Zarya shortly after. It's Zarya, not Zarya, Zarya. The Leonardo Permanent Multi-Purpose Module, or PMM, is a module of the International Space Station as well. It was flown into space aboard Space Shuttle on STS-133 on February 24th, 2011, and installed March 1st. Leonardo is primarily used for storage of spares, supplies, and waste on the ISS, which was until then stored in many different places within the station. It is also the personal hygiene area for the astronauts who live on the U.S. orbital segment. The Leonardo PMM was a multi-purpose logistics module before 2011, but was modified into its current configuration. It was formerly one of 2 MPLM used for bringing cargo to and from the ISS with the Space Shuttle. The module was named for the Italian polymath, Leonardo da Vinci. The Bigelow Expandable Activity Module, or BEAM, is an experimental expandable space station module developed by Bigelow Aerospace under the contract to NASA for testing as a temporary module on the International Space Station from 2016 to at least 2020. It arrived at the ISS on the 10th of April in 2016 and was berthed to the station also on the 16th of April at Tranquility Node 3 and was expanded and pressurized on the 28th of May in 2016. In December of 2021, Bigelow Aerospace conveyed ownership of the module to NASA as a result of Bigelow's cessation of activity. The International Docking Adapter is a spacecraft docking system adapter developed to convert APAS 95 to the NASA docking system. An IDA is placed on each of the ISS's two open pressurized mating adapters, both of which are connected to the Harmony module. Two international docking adapters are currently installed aboard the station. Originally, IDA-1 was planned to be installed on PMA-2, located at Harmony's forward port, and IDA-2 would be installed on a PMA-3 at Harmony's zenith. After IDA-1 was destroyed in a launch accident, IDA-2 was installed on PMA-2 on the 19th of August in 2016, while IDA-3 was later installed on PMA-3 the 21st of August in 2019. The Bishop Airlock Module. The NanoRacks Bishop Airlock Module is a commercially funded airlock module launched to the ISS on SpaceX CRS-21 on the 6th of December in 2020. The module was built by NanoRacks, Thales, Alenia Space, and Boeing. It was to be used to deploy CubeSats, small satellites, and other external payloads for NASA, CASIS, and other commercial and governmental customers. Nauka, Russian for science, also known as the Multipurpose Laboratory Module, upgrade, is the Roscosmos funded component for the ISS that was launched on the 21st of July, 2021. The original ISS plans, Nauka, was to use the location of the docking and stowage model, but the DSM was later replaced by the Razvet module and moved to Zarya's Nadir port. Nauka was successfully docked to Zvezda's Nadir port on the 29th of July 2021, replacing the Pirs module. It had a temporary docking adapter in its Nadir port for crewed and uncrewed missions until Pritchal arrived, where just before its arrival was removed by a departing Progress spacecraft. Pritchal is Russian for Pir, is a 4-ton spherical module that serves as a docking hub for the Russian segment of the ISS. Launched November 2021, Pritchal provides additional docking ports for Soyuz and Progress spacecraft, as well as potential future modules. Pritchal features 6 docking ports: forward, aft, port, starboard, zenith, and nadir. One of these ports, equipped with an active hybrid docking system, enables it to dock with the Nauka module. The remaining 5 ports are passive hybrids, allowing for docking of Soyuz, Progress, and heavier modules, as well as future spacecraft with modified docking systems. As of 2024, the forward, aft, port, and starboard docking ports remained covered. Pritchal was initially intended to be an element of the now-cancelled Orbital's piloted assembly and experiment complex. That's a mouthful. The ISS has a large number of external components that do not require pressurization. The largest of these is the Integrated Truss Structure, ITS, to which the station's main solar arrays and thermal radiators are mounted. The ITS consists of 10 separate segments forming a structure about 108.5 meters long. The station was intended to have several smaller external components, such as 6 robotic arms, 3 external stowage platforms, and 4 express logistics carriers. While these platforms allow experiments, including MISSE or MISSE, the STP H3, and the robotic refueling mission, to be deployed and conducted in the vacuum of space by providing electricity and processing experimental data locally, their primary function is to store spare orbital replacement units. ROUs are parts that can be replaced when they fail or pass their final design life, including pumps, storage tanks, antennas, and battery units. Such units are replaced either by astronauts during EVA or by robotic arms. Several shuttle missions were dedicated to the delivery of ROUs, including STS-129, STS-133, and 134. As of January 2011, only one other mode of transportation of ROUs has been used. The Japanese cargo vessel HTV-2 was delivered, and FHRC and CTC-2 via its exposed pallet. There are also smaller exposure facilities mounted directly to laboratory modules. The Kibo exposed facility serves as an external porch for the Kibo complex. A facility on the European Columbus Laboratory provides power and data connections for experiments such as the European Technology Exposure Facility and the Atomic Clock Ensemble in space. A remote sensing instrument, SAGE 3-ISS, was delivered to the station February 2017 aboard CRS-10, and the NICER, or NICER, experiment was delivered aboard CRS-11 June of 2017. The largest scientific payload externally mounted to the ISS is the Alpha Magnetic Spectrometer, a particle physics experiment launched on STS-134 in May of 2011 and mounted externally on the ITS. The AMS measures cosmic rays to look for evidence of dark matter and antimatter. The commercial Bartolomeo external payload hosting platform, manufactured by Airbus, was launched on the 6th of March in 2020 aboard CRS-20 and attached to the European Columbus module. It will provide an additional 12 external payload slots, supplementing the 8 on the Express logistics carriers, 10 on Kibo, and 4 on Columbus. The system is designed to be robotically serviced and will require no astronaut intervention. It is named after Christopher Columbus's younger brother. The MLM outfittings. In May of 2010, equipment for Nauka was launched on STS-132 as part of an agreement with NASA and delivered by Space Shuttle Atlantis. Weighing 1.4 metric tons, the equipment was attached to the outside of Razvet. It included a spare elbow joint for the European robotic arm and a ERA portable workpost used during EVAs, as well as RTO'd Ladon heat radiator and external hardware alongside the pressurized experiment airlock. The RTO'd radiator adds additional cooling capability to the Nauka, which enables the module to host more scientific experiments. The ERA was used to remove the RTO'd radiator from Razvet and transferred over to Nauka during VKD-56 spacewalk. Later, it was activated and fully deployed on VKD-58 spacewalk. This process took several months. A portable work platform was also transferred in August of 2003 during VKD-60 spacewalk, which it can attach to the end of the ERA to allow cosmonauts to ride on the end of the arm during spacewalks. However, even after several months of outfitting EVAs and RTO'd heat radiator installation, 6 months later, the RTO'd radiator malfunctioned before active use of Nauka. The malfunction, a leak, rendered the RTO'd radiator unusable for Nauka. This is the third ISS radiator leak after Soyuz MS-22 and Progress MS-21 radiator leaks. If a spare RTO'd is not available, Nauka experiments will have to rely on Nauka's main launch radiator, and the module could never be used to its full capacity. Another MLM outfitting is a 4-segment external payload interface called Means of Attachment of Large Payloads. Delivered in 2 parts by Nauka by Progress MS-18 and Progress MS-21 as part of the module activation outfitting process. It was taken outside and installed on the ERA aft-facing base point on Nauka during VKD-55 spacewalk. Robotic arms and cargo cranes. The Integrated Truss Structure, or ITS, serves as a base for the station's primary remote manipulator system, the Mobiling Servicing System, MSS, which is composed of 3 main components. Canadarm2, the largest robotic arm on the ISS, has a mass of 1,800 kilograms and is used to dock and manipulate spacecraft and modules on the USOS, hold crew members and equipment in place during EVAs, and move Dextra to perform tasks. Dextra is a 1,560 kilogram robotic manipulator that has 2 arms and a rotating torso, with power tools, lights, and video for replacing orbital replacement units and performing other tasks requiring fine control. The Mobile Base System is a platform that rides on rails along the length of the station's main truss, which serves as a mobile base for Canadarm2 and Dextra, allowing the robotic arms to reach all the parts of the USOS. A grapple feature was added to Zarya on STS-134 to enable Canadarm2 to inchworm itself onto the ROS. Also installed during STS-134 was the 15-meter orbital boom sensor system, which had been used to inspect heat shield tiles on space shuttle missions and which can be used on the station to increase the reach of the MSS. Staff on Earth or the ISS can operate the MSS components using remote control, performing work outside the station without the need for spacewalks. Japan's Remote Manipulator System, which services the Kibo Exposed Facility, was launched on STS-124 and is attached to the Kibo pressurized module. The arm is similar to the Space Shuttle arm as it is permanently attached at one end and has a latching and effector for standard grappling fixtures at the other. The European robotic arm, which will service the ROS, was launched alongside the Nauka module. The ROS does not require spacecraft nor modules to be manipulated, as all spacecraft and modules dock automatically and may be discarded the same way. Crew who use the 2 Strela, in Russian Arrow, cargo cranes during EVAs for moving crew and equipment around the ROS. Each Strela crane has a mass of 65 kilograms, or 100 pounds, roughly. A former module, Piers, or in Russian for Pier, was launched 14th of September 2001 as an ISS assembly mission 4R on a Russian Soyuz U rocket, using a modified Progress spacecraft Progress M-SO1 as an upper stage. Piers was undocked by Progress MS-16 on July 26, 2021, and deorbited in the same day to make room for Nauka module to be attached to the space station. Prior to its departure, Piers served as the primary Russian airlock on the station, being used to store and refurbish the Russian Orlan spacesuits. Fun fact, the Piers module is represented in this LEGO model, as the model was made for the 20-year anniversary in 2020. Power and thermal control. Double-sided solar arrays provide electrical power to the ISS. These bifacial cells collect direct sunlight on one side and light reflected off from the Earth on the other, and are more efficient and operate at lower temperature than single-sided cells commonly used on Earth. The Russian segment of the station, like most spacecraft, uses 28V low voltage DC from two rotating solar arrays mounted on Zvezda. The USOS uses 130 through 180 VDC from the USOS PV array. Power is stabilized and distributed at 160 volts DC and converted to the user-required 124 volts DC. The higher distribution voltage allows smaller, lighter conductors at the expense of crew safety. The two station segments share power with converters. The USOS solar arrays are arranged as four-wing pairs for a total production of 75 to 90 kilowatts. These arrays normally track the sun to maximize power generation. Each array is about 375 meters squared in area and 58 meters long. In the complete configuration, the solar arrays track the sun by rotating the alpha gimbal once per orbit, and the beta gimbal follows slower changes in the angle of the sun to the orbital plane. The night glider mode aligns the solar arrays panel to the ground at night to reduce the significant aerodynamic drag at the station's relatively low orbital altitude. The station originally used rechargeable nickel-hydrogen batteries for continuous power during the 45 minutes of every 90-minute orbit that is eclipsed by the Earth. The batteries are recharged on the day side of the orbit. They had a 6.5-year lifetime and were regularly replaced over the anticipated 20-year life of the station. Starting in 2016, the nickel-hydrogen batteries were replaced by lithium-ion batteries, which are expected to last until the end of the ISS program. The station's large solar panels generate a high potential voltage difference between the station and the ionosphere. This could cause arcing through insulated surfaces and sputtering of conductive surfaces as ions are accelerated by the spacecraft plasma sheath. To mitigate this, plasma contactor units create current paths between the station and the ambient space plasma. The station's systems and experiments consume a large amount of electrical power, almost all of which is converted to heat. To keep the internal temperature within workable limits, a passive thermal control system is made of external surface materials, insulation such as MLI, and heat pipes. If the PTCS cannot keep up with the heat load, an external active thermal control system, or EATCS, maintains the temperature. The EATCS consists of an internal non-toxic water coolant loop used to cool and dehumidify the atmosphere, which transfers collected heat into an external liquid ammonia loop. From the heat exchangers, ammonia is pumped into an external radiator that emits heat as infrared radiation. Then the ammonia is cycled back to the station. The EATCS provides cooling for all of the U.S. pressurized modules, including Kibo and Columbus, as well as the main power distribution electronics of the O0, of the S0, S1, and P1 trusses. It can reject up to 70 kilowatts. This is much more than the 14 kilowatts of the early external active thermal control system via the early ammonia servicer, which was launched on STS-105 and installed into the P6 truss. The ISS relies on various radio communication systems to provide telemetry and scientific data links between the station and mission control centers. Radio links are also used during rendezvous and docking procedures, and for audio and video communication between crew members, flight controllers, and family members. As a result, the ISS is equipped with internal and external communication systems used for different purposes. The Russian orbital segment primarily uses the Lyra antenna mounted on the Zvezda for direct ground communication. It also had the capability to utilize the Luch data relay satellite system, which was also in a state of disrepair when the station was built, but was restored to operational status in 2011 and 2012 with the launch of Luch 5A and Luch 5B. Additionally, the Voskhod M system provides internal telephone communications and VHF radio links to ground control. The U.S. orbital segment, or USOS, makes use of two separate radio links: S-band for audio telemetry commanding, located on P1 and S1 truss, and KU band, audio, video, and data, located on Z1 truss systems. These transmissions are routed via the United States Tracking and Data Relay satellite system in geostationary orbit, allowing for almost continuous real-time communications with Christopher C. Kraft Jr. Mission Control Center in Houston, Texas. Data channels for the Canadarm2, European Columbus Laboratory, and Japanese Kibo modules were originally also routed via the S-band and KU band systems, with the European Data Relay System and a similar Japanese system intended to eventually complement the TDRSS of this role. UHF radio is used by astronauts and cosmonauts conducting EVAs and other spacecraft that dock to or undock from the station. Automated spacecraft are fitted with their own communications equipment. The ATV used a laser attachment to the spacecraft and the proximity communications equipment attached to Zvezda to accurately dock with the station. The U.S. orbital segment of the ISS is equipped with approximately 100 commercial off-the-shelf laptops running Windows or Linux. These devices are modified using the station's 28-volt DC power system, and with additional ventilation, since heat generated by the devices can stagnate in the weightlessness environment. NASA prefers to keep a high commonality between laptops, and spare parts are kept on the station so astronauts can repair laptops when needed. The laptops are divided into two groups: the Portable Computer System, PCS, and Station Support Computers, SSC. PCS laptops run Linux and are used for connecting to the station's primary command and control computer, which runs a Debian Linux, a switch made from Windows in 2013 for reliability and flexibility. The primary computer supervises the critical systems that keep the station in orbit and supporting life. Since the primary computer has no display or keyboards, astronauts use a PCS laptop to connect as a remote terminals via a USB to 1553 adapter. The primary computer experienced failures in 2001, 2007, and 2017. The 2017 failure required a spacewalk to replace external components. SSC laptops are used for everything else on the station, including reviewing procedures, managing scientific experiments, communicating over email or video chat, and for entertainment during downtime. SSC laptops are connected to the station's wireless LAN via Wi-Fi, which connects to the ground via the Ku band. While originally this provided speeds of 10 megabits download and 3 megabits upload from the station, NASA upgraded the system in 2019 and increased the speeds to 600 megabits. ISS crew members have access to the internet. The living quarters and working space aboard the ISS is larger than a 6-bedroom house, equipped with 7 private sleeping quarters, 3 bathrooms, 2 dining rooms, a gym, and a panoramic 360-degree view bay window. The station provides dedicated crew quarters for long-term crew members. 2 sleep stations are located in the Zveda module, 1 in Nauka, and 4 in Harmony. These soundproof, person-sized booths offer privacy, ventilation, and basic amenities such as a sleeping bag, a reading lamp, a desktop, a shelf, and storage for personal items. The quarters in Zveda include a small window but have less ventilation and soundproofing. Visiting crew members use tethered sleeping bags attached to available wall space. While it is possible to sleep floating freely, this is generally avoided to prevent collisions with sensitive equipment. Proper ventilation is critical as astronauts risk oxygen deprivation if exhaled carbon dioxide accumulates in a bubble around their heads. The station's lighting system is adjustable, allowing for dimming, switching off, and color temperature changes to support crew activities and rest. Our total build time today is 2 hours, 3 minutes, and 34 seconds. If you have any interest in the life of an astronaut, I recommend giving Astronaut Dairies Year in Space a watch. Remember to like, subscribe, share, ring that bell, all the things for the YouTubes. Thank you.